Okay, let's see. It's 1:20. It's starting time. So I just sent out an email to everyone. Someone last time brought up World Mental Health Day on it's either Friday or this weekend, and the universities encouraged us to reduce the load on Friday. I think that's great. I'd love to reduce the load for myself included. Though it's kind of as I guessed, it wasn't very helpful. So we're supposed to let you out of synchronous classes, and this is kind of a synchronous class for those who want to show up, and it's asynchronous for those who don't want to. So I'm still required to record the lecture. So I'll still be here Friday talking to my computer screen and recording a video for both sections. And, you know, I don't post both of them. I post whichever one came out a little bit better that day. So you're welcome to show up if you want. If not, you'll watch the video in your own time, but that's really no different from what we do now. You show up if you want or watch the video asynchronously. So that's, oh, my phone dinged. Everyone's saying I'm calling them. Something must be wrong with my phone. I'm not calling anyone, but they're all saying, hey, are you calling me? Maybe I've been hacked. I don't know. Anyway, yeah, so that's not that big of a deal. So in other words, it's business as usual on Friday. I'll be teaching. You're welcome to show or watch the video later. Though what I will do is I'll move homework 5 again off the weekend. Homework 5 was originally due Friday. We moved it to Monday. I'll move it to Wednesday. And as I think I mentioned last time, and we'll see this time as we get into it, homework 5 is different than the other homeworks. It's a more challenging problem. It's essentially one large problem broken into smaller, more manageable chunks, and it's all math. And I know that intimidates some of you, but you know, I'll hold your hand through it. We'll get through it together, and you'll get a taste for what one of these a more real astronomy problem is like. And the problems do build on each other. It's more challenging. So instead of having that due Monday, I'll push that back to Wednesday. You don't need to. We'll get through it all today or maybe a little bit on Friday. But that gives you, you know, you won't have to spend the whole weekend trying to figure it out. I do encourage you to try to get it done a little bit early, just because it is challenging. And what I'm going to do is I'm going to move my office hours next week. I'll still have the office hours tomorrow for those who've already started it and may have some questions. And I'll move my office hours next week up from Thursday to Tuesday. And I'm moving the homework back to Wednesday. So that's another set of office hours right before the homework's due. People haven't really been making use of my office hours a little bit at the beginning, but sometimes nobody comes. It's okay. It's sad and lonely, but it's okay. I get other work done. But normally this homework is what draws a lot of people to my office hours. And so you get 2 of them. You get Thursday and you get Tuesday. Okay, so that's my plan there. Questions about any of that? That all sound acceptable? Okay, so try to enjoy your weekend a little bit now that some of the pressure's off. Let's see. Now, the next thing I wanted to do is a couple classes ago, I was talking about UNC telescopes, and I was talking about a radio telescope, and I wanted to demo it for you, but they had just taken it down for maintenance, and it turned out they kept it in maintenance until Monday. It's back online now, so I figured I'd redo that demo, and just, oops, slid you all over. 1 second. There you go. And just to remind you what we were targeting, it was this object here, the supermassive black hole. I think it's about 2 billion times the mass of our sun, at the center of the cannibalistic galaxy at the center of our galaxy cluster. Our galaxy lives in the outskirts of a cluster of galaxies. At the center, there's a big cannibalistic galaxy that keeps gobbling up other galaxies. And so its central black hole has grown quite large. Also timely because Nobel Prizes are being given out this week. And the Nobel Prize in Physics was given to three physicists and astronomers. One was Roger Penrose for his theoretical work with black holes. And the other two, I forget the one, but one is Andrea Getz, I believe, who discovered the black hole at the center of our Milky Way. Two of them so there are two with an observational component, and then Roger Penrose, who's kind of like the counterpart of Stephen Hawking. The two of them did a lot of things together. He won for theoretical work. Anyway, I have a cool Roger Penrose story, a little aside here. I met him when I was an undergrad, when I was your age. I was looking around my dorm room and it was getting pretty messy, and I figured I better clean this place up and take stuff out to the dumpster. And I did, and I went out to the dumpster with a pile of junk, and standing by the dumpster behind my dorm was Roger Penrose, who's now a Nobel laureate. And I said, "Hey, you're Roger Penrose." And he said, "Yes, I am," in his British accent. I said, "I'm reading your book. I just bought a book. He writes popular books." I said, "Wait right here. I'll go up and get it, and you can sign it." And I ran up as fast as I could and grabbed my book and came back. But when I came back, he was gone. I looked everywhere. I looked behind the dumpster. I looked in the dumpster. No Roger Penrose. Now he's a Nobel laureate. So that's my Roger Penrose story for what it's worth. Anyway. Okay, so I totally lost track. Yeah, I'm going to demonstrate observation of a black hole. Of course, black holes don't emit light, but all the stuff around the black hole, falling into the black hole, and also their jets of emission produced by this disk of material falling into the black hole makes a lot of radio waves. And we saw, a year or two ago, this picture of the black hole at the center of the Virgo supercluster, or the Virgo cluster. And we can see the event horizon, the region where even light cannot escape. Now, this was taken with a Earth-size interferometer. We can't achieve this kind of resolution with a little 20-meter diameter radio telescope, Green Bank Observatory. I think, yeah, that right there is what we'll be using. So imagine this, but blurred out tremendously. So let's give it a go here. So I'm at Skynet. Maybe I'll make this full size. I'm going to add a radio observation. And let's see, it is right here. I just happen to know. C3274, there's the galaxy, black hole buried somewhere in the center, spewing out tremendous number of radio waves. It's one of the brightest objects in the sky in the radio. It's observable from Green Bank right now. So I'll save and continue. That looks good. And I'm going to do a daisy pattern, which is a loop-de-loop over it. Again, these radio telescopes are 1 pixel cameras, so we're not going to get an image today, but I'll just pass over it a couple times so you can see that it's there. I'll do like a 3 degree. The beam on this is about 3/4 of a degree. So I'll go out about 3 degrees and then sweep back, and I'll do 4 petals of this daisy pattern. It's kind of a flower pattern. And I'll let it go for about 2 minutes, save and continue. I'll submit it. Okay, so it's in my list. Let's go to Skynet Live and see, make sure we have no problems with the telescope. So everything's idle. Okay, mount initializing. It's taken up my observation. Let's go to the Green Bank site and click on the Green Bank telescope. And this one's kind of cool. We get live feedback on this page. Unlike the optical telescopes where you wait for the image to come back, here we get a live response. So the crosshairs, I mean, the telescope is moving right now, and you can see it moving. It's already moved down to this position here. The little spike there is it initializing the camera, resetting the electronics. So that's a little fake signal. We have 2 channels here, orthogonal polarizations, but they basically do the same thing. Mount executing, which means it's starting to move. So I'll zoom in even more. You can see the loop-de-loop pattern. and it just passed over it, and it won't be really noticeable until these spikes get out of the way. The graph auto scales, and this is eating up all the dynamic range. There's a tiny little bump here that would become much bigger once this moves off the side. So we had one pass. Okay, one of the spikes is moving out. Okay, there we go. So this little box here is it's just testing and calibrating the equipment, but then I'm passing over it, and I just passed over it again. So you see every time I pass over it, we get this burst of radio waves. Now Siri says, I didn't get that. Could you try again? No, Siri. And let's see, we'll get 2 more passes. And it's kind of really bumpy and lumpy down below because the sun is actually really close in the sky right now. And the sun creates an interference pattern that messes up this region of the sky. And so we're seeing the outskirts of, it's like light bouncing off or diffracting off the support structure of the telescope from the sun. It's creating the undulations at the bottom. But the big peaks here are passing over that galaxy. And the only thing in the galaxy emitting a lot of radio waves is that central black hole. So timely demonstration given the Nobel Prize. Any questions about that? And if you're in the lab course, you actually have access. You could repeat what I've just done. We're saving this to video so you can have an example of it if you want to check out the brightness of some of the radio sources. Okay. I don't want to close that down completely. Save it for the next class. All right, now get rid of that. We have our warm-up question, which we'll come back to because we haven't gotten that far. We were in the middle, or actually mostly through the discovery of the solar system. And so we're up to the 20th century now. I'll finish that up, and then I'll start going through the math that you'll need for the homework. Once we've discovered a world, what do we do to characterize it? But still a little bit of our history. We'd gotten up to the beginning of the 20th century. So here we have Clyde Tombaugh, American astronomer working in the US Southwest. He was hired for a really boring project of just imaging the sky over and over and over again. This is back when they're using photographic plates. This is 1930 when he made his discovery of Pluto. And then he has to look at these plates looking for anything that's moving. And he found Pluto. Now, we've been finding lots of worlds like Pluto since, ever since, well, not ever since, but recently in the past decade or 2 or so. He just found one of them way, way early. And so it created this mess where we created another planet that we 80 years later took away, something close to 80 years later. But I'll tell that story. Here's his discovery image. 2 images, one taken January 23rd, one 6 days later, January 29th. And then he has to look at these. There are no computers to do this. You have to do it with your eye and with your brain, seeing if anything is like a new source of light, like maybe a star exploded, or a moving source of light. And the moving sources of light are usually asteroids or comets. It's rare that you find something that is a planet or something that at least back then they called a planet. But here it is. If you look over in this region, there's kind of this double star, and above it, there's a little triangle. The arrow's pointing to the bottom part of the triangle. You come over here, you see that little double star, and the bottom part of that triangle is gone. Instead, it's over here. You can see there's a bright one, medium, and faint. Over here, bright one, medium, and nothing. So this point of light has moved from here to here. And once you have, I think it's 3 of these images, you can characterize the orbit. You typically want more, but minimum is 3. You can determine the orbit. And indeed, it was going around the sun and is farther out than Neptune. Because once you measure how fast it's moving across the sky, and then you can figure out how long it takes to go around the sun. You have the orbital period. You can use Kepler's third to figure out how far it is from the sun. And it's farther out than Neptune. So he discovered a new world, a new planet, at least as they defined them back then. And it stayed a planet for a long time until we demoted it. Come back to that in a second, but just showing you the key telescopes of the day. He used a small telescope to discover Pluto, not this larger one here. If you're in the lab course, you're using small telescopes and you imaged Pluto and you went through a similar exercise trying to pick it out, the field of stars. Anyway, this is 1917. This is the beginning of California astronomy. This is the 100-inch Hooker telescope, Mount Wilson. In fact, it was almost, Mount Wilson was almost destroyed by fire just a few days ago, but my understanding is they saved it, and so the telescope's fine. And so it's still there. It's used really as an instrumentation testing facility. Now it's too close to LA. Back then, LA wasn't as bright as it is now. Then here's the Hale telescope, which you already know about. This was built in 1948, again, California astronomy. It's a 200-inch. So they went from a 100-inch mirror to a 200-inch mirror. And then in the 80s and 90s, they built the two Keck telescopes, which we've also talked about. And those are 400-inch mirrors or 10-meter mirrors each. And as we also talked about, this is now moving into the next century. Skipping ahead a little bit, we'll go back into the 20th century, but they're building a 30-meter class telescope, as are American astronomers and European astronomers building telescopes of this class. And that's what's going on now, and it will take about a decade to finish these projects. There you can see a size comparison. Now, in the 20th century, it was also the era of discovering planetary rings. Just like the century before, we were discovering planetary moons and asteroids. Here we're discovering planetary rings. Of course, we already know about Saturn's rings because they're so big and bright, but we learned that all the gas giants have rings, really thin, piddly little, barely there rings, but rings nonetheless. And these were discovered as part of our exploration of the solar system. We can send probes, beginning in the 70s anyway, or 60s and 70s, we were sending probes through the solar system and determined that the gas giants have rings. And as I mentioned the other day, this is now in the 21st century again, we're discovering rings around smaller bodies in the solar system. I think there are 3 of them so far, beginning with Chariklo, which is the largest object between the gas giants. I mentioned it the other day because Skynet played a key role in the discovery. Maybe I'll show you a little bit more about that because it's kind of fun. Here's a video. A star, and Chariklo is about to pass in front of this star, and so it will go dim. There's Chariklo's blocking it. But if you watch before and after, there, okay, it's repeating, so now it's blocking. If you watch, there. You may have seen a little dimming, real quick dimming, and that's the ring passing in front of the background star. And so I showed you this light curve before, the double ring. And think of it as a shadow of this little world and its double ring system passing across the Earth. And so all sorts of telescopes teamed up and, of course, detected the main object, but also we caught little glimpses of the ring from different parts in the cast shadow, and we're able to piece it together. And more objects like this are being discovered. So rings appear to be pretty common. Okay, moving into the 21st century. Those were the big features of the 20th century, some of it bleeding over into the 21st. And the biggest thing in the 21st century is the discovery of worlds beyond Neptune, some of which actually began in the 20th century. So these are not clean divisions. Here's the key player. This is Mike Brown of Caltech. There are a lot of teams out there trying to find these worlds out beyond Neptune. He hasn't found all of them, but his finger's in most of the pots. He's led most of the efforts, and if any one person can be singled out for credit, it's probably Mike Brown. And here's just some of the worlds. Of course, there's Pluto, which Tom Bogg discovered. And we can see Pluto has many moons around it, which we'll learn more about as we go through the course. But we've been discovering other worlds that are almost as big. Makemake, Haumea, Sedna. This one doesn't have a name yet, or at least when they made this figure, it didn't have a name. It may be named now. The International Astronomical Union sometimes takes their time in coming up with names. Quarwar, Orcus, Varuna, I think, is the next biggest one. There are about 20 or 30 of them now, worlds that we found out of decent size that we found out beyond Neptune. So you can ask the question, if Pluto's a planet, why isn't Makemake a planet? That doesn't seem fair. It's almost as big. If you're an alien flying into the solar system for the first time, seeing all these little worlds, you wouldn't say, oh, that's a planet, but those others aren't. So, maybe all of these should be planets. But then we run into the same problem that we had back in the early 1800s with the discovery of the asteroid belt, where they just started naming them all planets. They're objects going around the sun, but they're little objects. And, after a while, we realized it's too much. We shouldn't call all these things planets. And it seems that we're heading in the same direction, at least in the 1990s. It seemed that we were heading in the same direction with these worlds out beyond Neptune. Are we going to make them all planets? Are we going to demote Pluto and make it not a planet? So that's actually what we tried to do. In 1996, the International Astronomical Union got together and they tried to demote Pluto, saying it was a mistake. It's just one of these worlds that are out there. But then the letter writing campaign began, mostly from kindergartners and first graders, writing these sad, tear-filled letters. Don't take away our planet. It's our favorite planet. And presented with this international army of tiny children, astronomers buckled in fear and decided not to demote it, not at that time. And why do they love it so much? It's probably because of the Disney character, Pluto the dog, that also came out in 1930. And I can't remember if the planet was named after the dog or the dog after the planet, but it's speculated there's some connection there. And so, they just love the planet. Maybe they love it because it's an oddball. You have the gas giants, then you have this piddly thing out beyond them. So we gave in and did not demote it at that point in time. But then in 2005, Brown found another world. This one was later called Eris and has a moon dysnomia. At the time, he named it Xena. If you discover it, you can name it whatever you want, but then the International Astronomical Union changes it. He named it Xena and the moon Gabrielle because there's a popular show on TV, Xena the Warrior Princess, and Gabrielle was her sidekick. So I thought that was kind of cute. But the IAU said, no, we're not doing that, and renamed it Eris and dysnomia. Anyway, I'm trying to get this right here. It's the same size as Pluto, but more massive. Initially, we thought it was bigger and more massive, but more careful measurements suggest that it's pretty much the same size, to within a few kilometers, I think, but it is more massive. So if Pluto's a planet, then Eris must be a planet. And this forced us to reconsider the question, then why not Makemake? I love saying Makemake. Any excuse I can find to say Makemake, yeah, I go for it. But anyway, why not these worlds? And so they all met and they finally did it. They pulled the plug. They said none of them are planets. They demoted all of them to trans-Neptunian objects, TNOs. And there are different classes of trans-Neptunian objects that we'll learn about. But it wasn't a complete loss. They came up with this new category called dwarf planet. And so let me actually write down the distinction, what makes something a planet versus a dwarf planet. Go to the dot cam, come back to this in a second. And so to be a planet, you have to satisfy three criteria. You have to orbit the sun. 2, you have to have enough gravity and hence enough mass to pull yourself into a smooth shape. It doesn't have to be shape. There we go. It doesn't have to be perfectly spherical. Haumea, for example, from what we can infer, we can't take a great picture of these other worlds. We have to infer it by watching like how the light varies as it rotates. Sometimes it's brighter, dimmer, and we can infer, oh, it's not spherical, it's oblong. Sometimes more light's being reflected, less depending on its orientation. But Haumea is not spherical, but it's probably smooth. Based upon its brightness and its mass, we can measure its mass because it has moons going around it. We can watch those moons and figure out how massive Haumea has to be to make the moons move in that way. Based on our understanding of physics, it's probably pulled itself into a smooth shape, as has Makemake. These we're not as sure about. And then the third criteria to be a planet is you have to clear, this is new, you have to clear your orbit of debris. In other words, you have to be the dominant thing in your orbit, and all the other little things you've either absorbed them or scattered them out. And that clearly never happened in the asteroid belt, and it didn't happen out beyond Neptune. There's a bunch of little things, no one thing gained dominance. But that's to be a planet. If you satisfy just the first two, then we call you a dwarf planet. And Eris and Pluto and Makemake and Haumea, they all make that cut. Based upon what we know about them, they probably have enough gravity to pull themselves into a smooth shape. So all four of those are dwarf planets. So, you know, it's a sad story for Clyde Tombaugh. He had a planet and lost it. It was taken away from him. And a happy story for Mike Brown. He gained a dwarf planet, the biggest of the dwarf planets. But don't feel too bad for Clyde or too happy for Mike Brown, because in careful examination of their pictures, it's clearly the same guy just traveling through time, doing the same work for decades on end. So you win some, you lose some, right? But the happy part of the story, back to my favorite character in astronomy, is poor Giuseppe Piazzi with his lumpy forehead. Ceres, you recall, was a planet and was demoted all the way down to asteroid, but it now meets this new definition of dwarf planet. It's smaller than Eris and Pluto, but that's because it's made of rock. It's denser. Its mass is similar to Eris and Pluto, and it has enough gravity to pull itself into a smooth shape. In fact, we've been there and we know that now. And so it too is a dwarf planet. So he at least gets that. He gets a consolation prize after all these centuries. Okay, so that's the end of my history for the discovery of the solar system. Let's see, we had a little warm-up question, which I'm sure you can answer now that we've discussed it, but just out of curiosity, let's see what you guessed. Yeah, most of you got it right. There are 4 of them out beyond Neptune, and then 1 in the asteroid belt. And as we learn more about these bodies beyond Neptune, some of them may be added. So it's not set in stone. This could increase with time, and we're still discovering worlds out there. And in fact, we think there's a big one out there, more massive than the Earth, based upon how it's scattered some of the smaller things over time. We just haven't found it yet. But if it's out there, it's really far out there, maybe very hard to see. Okay. So now we're going to switch over to what you do once you found one of these things. So suppose you discover something out there moving around the sun, then how do we figure out its bulk properties? In the textbook, you have a table. This is a rather old version of it, 2008, but I'm sure they have an updated version in the textbook and with some of the numbers updated. Like number of known satellites, that's changed a lot, but most of the rest of it is pretty much the same. So here we have planets, we have Ceres there representing the asteroid belt, we have Pluto representing the trans-Neptunian objects, most of which are in what we call the Kuiper belt. We have a representative comet and the sun down here. Of course, there are many other things, but just in this table. And then we have a bunch of numbers, the semi-major axis, the orbital period, the mass, the diameter, number of known satellites, rotation period, and average density. How do we know these things? Kind of the bulk characteristics. Fine details, we'll get into that as we talk about the planetary missions to get close to the planets and learn more about them. But just bulk properties. You can figure most of this stuff out from just a few basic observables. And that's kind of the goal of homework 5, given 4 basic observables. And those are how long it takes to go around the sun. What is its angular size? If it has a moon, how long does it take to orbit? And how far away is it from its planet in some measure of that angle? Given those observables, you can actually calculate the rest of this. So we're going to go through that process of how to do it. So let's take each of these one at a time. We'll get through probably most of them today, but maybe not all of them. And we won't tackle them in order. Let's just start with orbital period here, because that's a pure observable. That's pretty easy. I'll be going back and forth with the dot cam. So first, let's talk about orbital period. Again, this is one of the observables. And it's observable because you can, one thing you can do is just wait. You discover something, it's moving, you could wait for it to go completely around. And then you know its orbital period. Now, if you just discovered something in the outer solar system, you might be waiting centuries, and that's kind of boring. So you don't actually have to do that. All you really have to do is measure how fast it's moving. And in fact, you had a question like this in one of your earlier homeworks. If it's moving 1 degree per year, how many years does it take to orbit the sun?
360.
360. There are 360 degrees in a circle. So you don't have to wait for it to do a full cycle. You can just measure its angular rate of motion and figure it out. You do have to make little corrections because you're observing from a planet that's also moving around the sun, and that messes it up a little bit, but those are corrections we know how to do. So you watch it and you extrapolate. And normally extrapolation is something to be cautious about, but we understand the physics of what it's doing very well. And timing is something astronomers do very well, or anyone. We can measure time very, very accurately and precisely. Okay, so let's look at some of these orbital periods. Here's the Earth at 1 year. That's how we define a year, 1 orbit around the sun. But Mercury is about 1/4 of a year, Venus about 2/3 of a year, Mars 2 years, things in the asteroid belt about 5, Jupiter's 12, Saturn's 30, then we're getting up to pretty long numbers as we get into the outer solar system, centuries. And with comets, it can be thousands of years. In fact, Hale-Bopp, the comet in this table, is considered a short period comet. Some comets can be much, much longer than that. Okay, so that's orbital period.
I have a question.
Yeah, go ahead.
Orbital period. Are we just assuming that all these orbits are like perfect circles? What if it's like a really like steep ellipse? How do we calculate that?
Yeah, so if you have 2 observations, you can calculate an angular rate, and that's enough if it's a circle. But if it's elliptical, that's another parameter, so you actually need a 3rd observation. If you get 3 observations, you can calculate not just the semi-major axis, but also the eccentricity of the orbit, as long as they're well separated. The more observations, the better, but that's the minimum.
Okay, thank you.
Cool. Okay, let's do orbital semi-major axis next. This one's also fairly straightforward. Let's see, orbital period, we denote that P. Orbital semi-major axis, as you know, we denote that A. And these are calculated. Once you know the orbital period, you can calculate the semi-major axis. using Kepler's third law, p squared is equal to a cubed. So a is equal to p to the 2/3. Again, you have to remember to use consistent units. If you measure the orbital period in years, the semi-major axis comes out in AU. And we'll want to convert that into something more meaningful, kilometers. But let's take it in 2 steps. Let's first just look at the AU in the table. Again, Earth is 1 AU from the sun by definition. Venus is at 0.4. Sorry, Mercury's at 0.4, Venus at 0.7, Mars 1.5. The asteroid belt is high 2s. Then it's 5, 10, 20, 30, 40 as you work your way out. So bigger and bigger gaps until you get at towards the end, then it's a little bit more compressed there. This particular comet is at 180, but again, they can be much, much farther as well. But that gives you kind of an idea. It's an expanding scale where some planets are really, really close to the sun, and those are the terrestrial worlds. Then we have the asteroid belt between Mars and Jupiter. And then the gas giants very much spread out. And then out beyond Neptune, we have the Kuiper belt, which is the primary location of the trans-Neptunian objects. You do have objects out here that are not part of the Kuiper belt as well, but they're primarily in the Kuiper belt, including Pluto and Makemake and Haumea. Eris, not so much, we'll see. I'm trying to remember if Eris counts as, I'll look it up, but it's a little bit farther out, stranger orbit. Okay. Now that's relative. You know, the astronomical unit gives you the relative spacing relative to Earth. But for some of the other calculations we're about to do, we need to put this into a more definitive unit, such as meters. So meter, if we can do it in meter, that's what we call absolute spacing. And we talked a little bit about how to do this. We need to measure the number of meters in the astronomical unit. So 1 AU is how many meters. And there are 2 ways, as we talked about in lesson 2, that you can do this. One is parallax, one is radar ranging. In both cases, we talked about it in the context of doing it to Venus at closest approach. You could do it with other planets or planets not at closest approach, but it's easiest to think about measuring the parallax to Venus when it's as close to Earth as possible, or radar ranging, bouncing radio waves off of Venus when it's as close to Earth as possible. And then you can calculate how many meters in an astronomical unit. Now, for the parallax case, if you're in the lab course, lab 4, you're doing that right now. So in this homework, we're going to try the other case, radar ranging. And we worked through the math of this in lesson 2, but I'll just repeat it here really quickly. It's a distance equals speed times time problem. Here we have the sun, here we have Venus, here we have Earth, here we have them at closest approach. So imagine sending some radio waves, which it's just a form of light, so it travels at the speed of light from Earth, bounces off Venus, and comes back. If Venus is 0.7 AU from the sun, and Earth is 1 AU by definition, and at closest approach, we're about 0.3 AU apart. And you'll do this calculation in the homework a little bit more precisely with an additional decimal point. So I'm just doing it roughly to help you out right now. But we figure out how long it takes to travel this distance. So if distance is speed times time, the distance we were traveling is 0.3 AU there and 0.3 AU back. The speed of light is 3 times 10 to the 8 meters per second. Time of flight is about 300 seconds. Again, I'm rounding things off. You'll do it more precisely in the homework. But the seconds cancel out. So you have something in AU on this side, something in meters on this side. You can divide both sides by 0.6. So this cancels with that, and we have 1 AU equals some number of meters. I won't calculate it here. You can. I'll make that bigger for you just for a second as you're copying stuff down. And you'll do that in the homework. In fact, that's the first 2 questions in the homework. We'll use Venus at closest approach and figure out how many meters in an astronomical unit, because we'll need that for the rest of the problem. Now, the rest of homework 5, I introduce a new world. I just made it up. I made up an object. Maybe it's a planet. I'll refer to it as a planet. I think I call it Planet X in the homework. But it's your job to figure out what kind of planet it is. And if it even is a planet, maybe it's an asteroid, or maybe it's another star orbiting the sun that we never noticed, or it's just a fictitious world that I made up. And I'm going to give you its basic observational properties, and you're going to calculate things like how far it is from the sun, how big it is, how massive it is, its density, its likely composition. So I'm going to work you through those now. So all the rest of the questions in homework 5 are connected. It's all about this planet X. But keep in mind, this happens all the time. We discover new worlds out beyond Neptune. I'm not promising the one I made up's beyond Neptune or that it's a Kuiper Belt object or anything like that. But in reality, we're discovering new worlds beyond Neptune all the time, new asteroids all the time. And every time we make one of these discoveries, this is the process we have to go through to do its basic characterization. So let's start on this table with, we'll come back to mass. Let's start with diameter, how big it is. And here things are listed in Earth diameters, but how do we know that? Okay. So what we do, I'm gonna switch to a clean sheet here, is we start by, let's see, this is diameter. And we start by measuring its angular diameter. That's the observable. So if I keep track of observables, I'll put them over here. We have the orbital period P. That's the first thing. We discover a new world. We figure out its orbital period. And from that, we can figure out how far it is from the sun. So that's observable number 1. Observable number 2 is the angular size. And from this and how far it is from us, we can figure out its physical size. So to figure out its angular size is super easy. We just take a picture. Suppose you take a picture with one of the prompt telescopes. Our basic prompt system has a field of view of 10 arc minutes. Suppose you take a picture of it there. Maybe there's some stars or moons or things in the background, but you can measure its angular size. If this is 10 arc minutes, what I drew here is maybe, in this case, 1 arc minute. But for whatever it is, you can just measure it off the image. That's the angle on the sky. Now, to convert that into a physical size, we have to use this geometry that we've seen before. And if you're in the lab course, you used it in lab 2 and lab 3, and you're using it again in lab 4. We saw it in this course when we were talking about parallax. This is just a different application of it. Here, we have someone standing on Earth, looking at this body over here. Nothing's to scale, of course. The object would probably be bigger than Earth and much farther away. But anyway, its angular size, that's this angle theta. That's the 1 arc minute I drew in this particular example. Its angular size, its angular diameter, as a fraction of 360 degrees is going to be equal to its physical size as a fraction of this big circle. A fraction of the circumference of that big circle. So let's write that down. So theta, the angular diameter, as a fraction of 360 degrees, is the physical diameter, something like meters, divided by the circumference of that big circle, and circumference is 2 pi times the radius, and the radius of this circle is the distance of the object from us. 2 pi distance. So not the distance from the sun, but the distance from us. And in the homework, we do this at closest approach. So let me just ask you, if an object is 10 AU from the sun, suppose a circular orbit, then how close does it get to Earth at closest approach? How many AU?
Would that be 9 AU?
That would be 9, yep, because the Earth is 1 AU from the sun, so at closest approach, we're 1 AU closer to it than it is to the sun. So you'll want to keep that in mind in the homework. I think in question 3, you figure out how far it is from the sun. In question 4, in AU, in question 4, you figure out how far it is from the Earth in meters. You convert it from AU to meters using your calculation of the AU from question 2, but how far from the Earth in meters? Be sure to subtract off 1 AU. Anyway, that's the distance, and distance from Earth, because we're taking the picture from Earth. Well, again, this is an observable. This angular size is easy to measure. Distance from Earth, that comes here from question 4. You'll be in meters, so you'll be able to calculate the diameter of the planet in meters. Get a physical size for it. And then, let's see, that is our question 5 in the homework. And then in question 6, it's just going to be a conversion. The way this homework goes is you have a tricky calculation and then an easy conversion, then a tricky calculation and an easy conversion. And we're going to convert it from meters to Earth diameters and also to AU. We'll use that, a planet's going to be a really small number of AUs, but we'll use that in an upcoming problem. But the key thing is you're going to convert it to Earth diameters, and that will begin to give you a feel for what kind of object this is. Is it another terrestrial world? Is it a gas giant? Is it an asteroid? Once we put in Earth diameters, you have a feel for how big it is compared to the size of the Earth. Let's take a look at some objects in our solar system here in Earth diameters. Again, Earth is 1 Earth diameter by definition. That Mercury is about 38% the size of the Earth. Venus is almost the same size as the Earth. We call Venus our sister planet because of that. Same size, similar mass, as we'll see, similar density, composition. We thought it may be a future destination, a future world for humanity, until we eventually went there and realized that it's hot as hell. It melts metal. And so, it's not going to be a future destination for us, and not for a very long time anyway. But it has similar bulk properties. The moon is about 27% the size of our planet, so a little bit smaller than Mercury. Mars is half the size of our planet, so not much bigger than Mercury. Everyone thinks of Mars as this big, important world because that's where we're traveling to. That's humanity's first destination other than the moon. But it's not a big world like Earth or Venus. It's a small world, kind of like Mercury or the moon. Ceres is quite tiny, but then you get into the gas giants, where Jupiter and Saturn are about 10 times the size of our planet. Uranus and Neptune are about 4 times the size. Pluto's pretty tiny, about 20%. Comets are minuscule. And again, we know the sun is about 100 times the size of the Earth. Okay, it is 2:09. That much there will get you through question 6 of the homework. So I encourage you not to put it off the last minute. Start working through those 6 problems. And Friday, I'll pick up with number 7, which is probably the toughest one in the homework, the mass. And I'll get you through the final questions, the math that you need to figure out what kind of world you're looking at. And then we'll switch back over to story time, and I'll tell you about the exploration of the solar system. Okay, I will stop there and stick around for questions.
Thank you.
My pleasure.
Thank you.
Thank you.
Can you go back to your other page of notes when you were doing like the D equals V times T thing?
Yeah,
That was actually what I wanted to inquire about as well.
yeah, it's
Thank
kind of
you.
rushing at the end a little bit. So you ended the same place as the other section.
And that's 0.6, right?
Yep, 0.6. In the homework, it'll be more precise, or like 0.5 something or other. But it's whatever it needs to be to cancel out this. Double the distance between us and Venus at closest approach. So you get 1 AU by itself.
Thank you so much.
Sure, my pleasure.
I'll still
Yeah,
I'll get distracted and I can't like listen and write. And so I just like
Of course, you always have screen capture as well. That's something you
Yeah.
want to think about.
being able to go back is super helpful.
And
kinda,
the
like,
videos are
watch-
there as well.
Yeah, because either that or like I go back to my notes and they don't make any sense because I was writing too fast.
Yeah.
So that was for the first 6 problems.
Yep, that will help you get through the first 6.
Can you show me which one refers to number 5? I didn't write it down.
Number 5 is the calculation of the diameter of planet X in kilometers.
Oh,
That's
okay, thank
using
you.
this equation here. It's like every other one's a tricky calculation, and then you have an easy unit conversion, then a tricky calculation, then an easy unit conversion. They kind of alternate.
Thank you so much, Dr. Reichart.
My pleasure.
Yeah, thank you. Have a good one.
You too.